Good evening, ladies and gentlemen, including our live stream audience that we have with us tonight, I believe. My name is Gerhard Velitis. I'm President of the Astronomical Society of South Australia, and it's my pleasure to welcome you to tonight's meeting. It's going to be a good one. Some preliminaries first. COVID is still with us, and we recommend a precautionary approach. Certainly, from personal experience, I have friends who have recently been in isolation, so it's still an issue out there. So please adopt a precautionary approach. Please switch your phones off or on silent mode for tonight's meeting, and in the event of any emergency, the primary exit is the way you came in, through the back, or alternatively through the doors on your right, which will take you out back through the way you came. If you need to visit the facilities, they're also through the door on your right, well to the back of the corridor and around the corner. But make sure you come back through the correct door when you return, because there are a couple of false entrances that you might get tangled up in otherwise. So everyone, welcome to our monthly meeting. Our mission is to observe, understand, share and enjoy the wonders of the universe. Now, could I have a show of hands for visitors here who are not members of ASA? Just a rough guide, so yeah, a dozen or so. I'll have more to say later, but obviously I encourage you to join our wonderful organisation. The Astronomical Society of South Australia acknowledges and pays our respects to the Kaurna people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationship of the Kaurna people to country, and we respect and value their past, present and ongoing connection to the land, sky and cultural beliefs. Tonight's program, we will have our main presentation, after which I'll conclude with announcements and upcoming events and supper at the back. So without further ado, let me introduce tonight's speaker. Tony Thomas, is a theoretical physicist who is the 6th person to hold the Elder Chair of Physics at the University of Adelaide, which was first held by Sir William Henry Bragg, Nobel Laureate. He is a chief investigator in the Australian Research Council, Centre of Excellence for Dark Matter Particle Physics, having previously served as Associate Director of the ARC Centre of Excellence for Particle Physics at the Terascale, as well as Director of the Adelaide Node. From 1997 to 2004, he was Director of the ARC Special Research Centre for the Subatomic Structure of Matter. He served as President of the Australian Institute of Physics from 91 to 93 during the preparation of the first strategic plan for physics in Australia. Within the University of Adelaide, Professor Thomas is Director of the University Research Centre for Complex Systems and the Structure of Matter. From 2009 to 2015, he held an ARC Australian Laureate Fellowship. During the 6-year period, 2004-09, Professor Thomas served as Chief Scientist and Associate Director for Theoretical and Computational Physics at the US Department of Energy's Thomas Jefferson National Accelerator Facility. Now, I'm sure you've heard of some of those places. They're at the top level of what they do. He's currently the Vice Chair of the Asian Nuclear Physics Association and past Chair of the IUPAP Working Group on International Cooperation in Nuclear Physics, having served as its inaugural chair for the first 6 years. As chair of the Working Group 9, he played a key role in the preparation of a roadmap for nuclear science prepared by a working group of the OECD Global Science Forum, again working at the top level. Amongst the academic awards he's received, we mentioned the Harry Massey Medal from the UK Institute of Physics, the Thomas Rankin-Lyell Medal, from the Australian Academy of Science, and Alexander von Humboldt Forschungspreise, the inaugural Silver Jubilee Convocation Medal from the Flinders University of South Australia, and the Walter Boas Medal of the Australian Institute of Physics. Ladies and gentlemen, we have a very highly credentialed speaker with us tonight. Please make welcome Tony Thomas.
Thanks for the kind introduction, Gerhard. So this should work, should it, if I...
I hope that from...
Oh, from there.
Yeah, from...
No, that's okay.
And you also have a red dot.
Okay. Now that might be better for those online. Okay. So thank you for leaving some time for my talk. That's great. I didn't realize you were going to read it all. As you may have guessed, I'm not an astronomer, so I apologize for those of you who are astronomers, but I enjoy what little I know, and what I do know is a little bit about the theoretical ideas about the structure of neutron stars. So the outline of this talk is I'll tell you, first of all, I'll bamboozle you with numbers to convince you that these things are the most remarkable objects you could imagine. We'll then talk a little bit about their discovery, their structure. I'll show you more than you want to know probably about their structure. And then I'll talk a little bit about how we learn about that structure. And I'll also touch on dark matter and dark energy, but not too much. So, what are neutron stars? Well, they're objects with a mass twice the mass of up to twice the mass of our sun, roughly. But their radius is just 12 kilometers or so. Now, that's 60,000 times smaller than our sun, which weighs 700,000 times more than the Earth. So these are incredibly dense objects. There's a lot of them in the Milky Way. I was shocked that there are probably a few hundred million in the Milky Way. And about 5% of those are in binary systems. The interest, from my point of view, is that they contain the most dense matter in the universe. You can see the number there, 1 million billion grams per cc. It's a little easier to imagine a matchbox that weighs 3 billion tons. That's the density of the matter at the core of a neutron star. It's an incredible state of matter. Gravity at the surface, 200 billion times gravitational strength on the surface of the Earth. Pressure, 10 to the 29. Now, I know everyone's not happy with scientific notation, but the pressure in the core, and we'll talk about that a little bit more later, is 10 to the 29 times atmospheric pressure. To give you an idea, to paraphrase The Hitchhiker's Guide to the Galaxy, the universe is a very big place. And 10 to the 29 millimeters is the size of the visible universe. So 10 to the 29 is a very big number. It's a huge pressure. Sorry, wrong thing. Okay. They can rotate, and they can rotate very fast. The fastest is more than 700 times a second. How are they formed? They're formed when a star with a mass somewhere in the range 8 to 25, sometimes you might read 8 to 40 times the mass of our sun. If they're lighter than that, they tend to leave a white dwarf. They don't leave a neutron star. If they're heavier than that, they leave a black hole. But there's this sweet spot where what they leave behind is a neutron star. The energy released is, and here I tried to do away with scientific notation for a short time, it's this amount more than a nuclear weapon. The explosion is as bright as 6 billion suns. Now, from the point of view of a theoretical physicist, to understand them, we need quantum physics, we need astrophysics, we need special relativity, we need general relativity, and we need nuclear and particle physics. That's what makes it fun. Many of you think that's fun? Gary, you think it's fun, don't you? So, here's a supernova appearing. A beautiful photograph. Galaxy on the left, without a neutron star, without a supernova, and then suddenly there's a bright spot. where a star exploded. To understand a little bit of history, we go right back to the beginning. The discovery of the atomic nucleus was about 115 years ago by Rutherford. A very simple experiment. He took alpha particles, something that Bragg played with when he was here in Adelaide, and fired them through a gold foil. It's hard to imagine something simpler. And most of the time, they went straight through. But occasionally and remarkably, they came backwards. And Rutherford drew the fairly simple conclusion that matter's mainly empty space, but there are hard lumps in there, which are very small. And those heavy lumps were the atomic nucleus, about 100 million times smaller than the atom. So surrounded by empty space and then a large distance away by electrons. At the time when Rutherford discovered the nucleus, no one had any idea what could hold it together. There was no idea. The only force known was the Coulomb force, and the only particles were the proton and the electron. No idea what could hold the nucleus together or how it could be so small. And then some 20 years later, Chadwick discovered the neutron. And after that, there were a whole bunch of particles started to be discovered. But the neutron was crucial. The neutron has almost the same mass. It's just a tiny bit heavier than the proton, but it has no charge. And within a year of that being, of the neutron being discovered, Baader and Zwicky was apparently quite an interesting character, extremely obnoxious, loud-mouthed, but clearly not a bad physicist, because he and Baader suddenly realized that stars might be able to explode, and if they did, you could leave behind something that contained these newly discovered neutrons. And that's 30 years before these objects were discovered. That was absolutely remarkable idea. So what about the discovery? Well, this is either fun or sad, or if you're, depending on your point of view, expected. The young lady on the left, young at the time, Jocelyn Bell, found what she called scruff on the paper charts, and some of the paper charts were 30 meters long, that looked like noise. And her supervisor, Anthony Hewish, was convinced it was noise, until finally she convinced them that it tracked with the movement of the stars and that it wasn't just noise, maybe it was something else. It was a radio signal at about 81.5 megahertz, and you see the radio receiver there, which was developed by Hewish and his people. And so the Nobel Prize for this discovery, which was called a pulsar by a reporter for the Daily Mail, I think it was, for pulsating radio source. So that's the origin of the name pulsar, because what they saw, and actually for a while it was labeled Little Green Man #1, because it was a regular beep of a radio signal that looked like it might have been sent by some intelligence far away. But it wasn't. Now, it's amazing in the history of science how many things can happen at the same time, because Jocelyn first realized what this was, or thought she realized what it was, on 28th of November 1967. But just before it, earlier in November, an Italian physicist had said maybe if these neutron stars of Baader and Zwicky existed, they might have large magnetic fields, and when they're spinning, charged particles might move along those fields and they might radiate, and you might see that radiation. So in the same month, 30 years after the proposal, two people, well, one person thought you might see these things and another one discovered them. Now, the Nobel Prize was very controversial. It was awarded to Hewish and Ryle, who, according to Jocelyn, met quite often with her excluded to discuss it. You have to say that when the Nobel Prize was announced, she said that it was probably appropriate that Nobel Prizes not be given to students. On the other hand, Nobel Prizes are given for discoveries, and it was she who basically made the discovery. So, but she had many more awards in her life, but that one she missed out on. And you might say it's because she's a woman in science, and that may have had something to do with it. The pulsar that they saw was in the Crab Nebula, which you see a picture of there, coming from a supernova explosion in 1054. So as our Italian friend Pacini had said, not Puccini, Pacini, these neutron stars can be surrounded by extremely strong magnetic fields, as high as 100 million to 10 to the 15 times the field of the Earth. And charged particles, and so as the neutron star rotates, the magnetic field is not necessarily aligned with the rotation, with the pole, and charged particles coming along those magnetic field lines are being accelerated. So they radiate all sorts of electromagnetic radiation, including radio. And so that's how they were seen. Now, how does a neutron star form? Well, you have a star with mass 8 to 25 times the mass of our sun. That's this first picture. It's burnt up all of its hydrogen and its helium, and it makes carbon and oxygen, and eventually gets to iron and cobalt, which have the biggest binding energy per neutron or proton of any nucleus. And after that, the formation of new nuclei has to stop. And when it stops, the energy released in making new nuclei slows down. And when the energy release slows down, so does the pressure. And gravity takes over. Gravity, which is usually pretty weak, takes this huge star, which by now has grown very large, and it collapses. So what we see in the second slide is with the reduction in pressure, as all the nuclear fuel is used up, the pressure drops and the matter is drawn in by gravity. However, when the matter in the center, the so-called core, gets to be dense enough, it starts to feel a very strong nuclear repulsion, and that starts a recoil, indicated in red. So you have matter still falling in, but you also have matter being bounced out by this very hard core. And that forms a shock wave, and the shock wave goes out, and that shock wave is irradiated by all the neutrons and neutrinos released in this process. Now remember, the amount of energy being released when this happens is 10 to the 44 times the energy released in a single atomic bomb. It's a huge amount of energy being released. And in this bath of neutrons, in the matter being forced out in this shock wave, heavy elements are formed. I'll come back to that at the end of the talk, because for many years, this was the only source we knew of elements heavier than iron and cobalt. So here's a textbook view of a neutron star. It's wrong, of course, and it's not to scale, but there's a surface, and the surface is interesting. The outer crust is nuclei, but they're very strange nuclei. They're compressed, and the atoms actually can be linear because of the strong magnetic fields. The nuclei have more neutrons, so they're often unstable nuclei. Slightly inside that outer surface, there is a more complicated nuclear structure with nuclei and neutrons, often referred to as a pasta because of the way things are organized. And then, but notice the scales, that's only 0.8 kilometers in 10 or 12 kilometers. And inside it, there's the core. And one thing we know is there are neutrons and protons and electrons, and the muon, which I'm sure you've all heard of, which is there for reasons we don't understand. It's like an electron, but it's 200 times heavier and feels the Coulomb force. And then in the middle, we have no idea. We have ideas, but we have no proof. We have no idea what's in there. And that's part of the fun of dealing with this problem. Now, there won't be too much maths in this talk, but I felt I needed to show you this. dP is the small change in pressure at some distance from the center of the star. It changes, so the small change in pressure when you move a distance dr. So dr is a small distance. When you move from here to here, the pressure changes by dpr. And that has a minus sign. So as you move out in radius, the pressure drops. The change in pressure is negative. And it's proportional to the energy per unit volume, the pressure, the mass inside radius, and the mass includes rest mass. It's the energy, total energy inside there, and the pressure term. So if you know the energy density, the energy per unit volume of the matter, and the pressure as a function of the pressure, or the pressure as a function of the energy density, you have everything you need on the right-hand side. So you make a guess, you make an assumption of the density at the center of the star at r equals 0, and you step out, and at each step the pressure goes down. And when the pressure gets to 0, that's the edge of the star. So that's the solution of the Tolman-Oppenheimer-Volkoff equations, invented in 1939 using general relativity. The relation between pressure and energy density is the so-called equation of state. But I've just told you that the density in the center of a neutron star is bigger than anything in the universe, including the center of an atomic nucleus. So we need to know this equation of state, the relation between the energy per unit volume and the pressure at densities which don't exist anywhere but in a neutron star. How do we learn about that? Well, one attempt to do that is to take nuclei. And so this is a picture of Brookhaven National Laboratory, and the pictures are taken from the STAR experiment. You get an idea of the scale of the experiment. This is a person adjusting something in the center of the star detector. The picture on the right shows what happens when two gold nuclei smash into each other at very high energy, and each line is some particle that's emitted. There are hundreds of them, and you have to be able to track those electronically. And from that, you hope to learn something about the relation between pressure and energy density. The reason you get such high densities, at least schematically speaking, is when a nucleus is going extremely fast, and these have energies 200 times the rest mass energy of the proton, the nuclei are no longer spherical, they're basically pancakes. And so you take these two pancakes, smash them into each other, and look at the rubbish that comes out. And from that, you try to understand what happens when matter forms something of very high density, when very high density matter is formed. There's similar experiments at CERN with the so-called ALICE detector, but that's performing experiments at much higher energy. But once again, you see huge numbers of particles produced, and once again, you get an indication of the size of the detector used to get this information. Now, there are two problems with what comes out of those experiments, which are the best we can do on Earth to learn about the equation of state, the relation between pressure and energy density. First of all, there is some controversy over what density you actually reach in the collision. And it may only be half as large as what I'm showing below. So this is from almost 20 years ago, but it's probably the best we've got. This is pressure. Don't worry about the units. They'll be meaningless to you, but I'll say more later. Pressure against the density of matter. Let me just say, nuclear matter density is just here, 0.16. So up here, we're at 3 times the density of an atomic nucleus. And at that density, this is the region of pressure deduced from these experiments. And you see some various theoretical calculations which agree with that data. But remember, the interpretation of the data may not be as accurate as it looks on here. But there's another issue. And here, if you'll forgive me, I wanted to just introduce you to one topic that's controversial. It's something that a lot of people are worried about at the present time. And it's the so-called hyperon puzzle, and I'll try to explain that to you simply. And it relies on something called beta equilibrium. So you've all heard of beta decay. You know that carbon-14 decays by beta decay, which is the weak force. Now, I told you that neutron stars are quantum mechanical objects. The first thing that one has to remember is that in quantum mechanics, there's a Pauli exclusion principle. And that tells you that if you have neutrons, only 2 of them can have the same momentum. And that means as we add more neutrons to form a more dense medium, the momentum the neutrons have gets higher and higher, because only 2 of them can go into the lowest, 2 go into the next momentum, 2 into the next, and we build up to a very high momentum. Eventually, that leads to a high energy level of neutrons. And at some point, the energy of the last neutron is greater than the mass of a strange particle. Now, what's a hyperon? In a hyperon, we've taken a proton and replaced one of its up quarks by a strange quark. So these are things that don't occur on Earth, except in experiments at nuclear particle physics labs. But we know a lot about them on Earth. We know a lot about them as free particles. We know that they have a lifetime of only a few nanoseconds, so a 1,000 billionth of a second. They don't live very long, but on the scale of strong force, that's very long. They can only be formed by the weak force, by a process called beta decay. But the time scale for that is nanoseconds, and a neutron star, is formed in roughly a second. This expansion, collapse, formation, explosion, leaving behind a neutron star, the formation of the neutron star is of order a second. And so that's a very long time compared with the weak force. So we expect to make hyperons, these lambda particles. So here's a little picture of what I just told you. We have a neutron with 0 momentum. We can only, an energy level with only 2 neutrons, which is all we can put there because of quantum mechanics. The next momentum level, which has a slightly higher energy, we can put 2 neutrons, 2 neutrons, 2 neutrons, 2 neutrons. We keep adding neutrons, and the energy goes up, because as the momentum goes up, the energy goes up. And sooner or later, the last neutron you've added has a higher energy than the mass of this strange particle containing a strange quark. And so this decay becomes possible, even though it involves a weak interaction. And this can't happen in those collisions in laboratory experiments, because the time scale for those is much shorter than the lifetime of the hyperons. So we know on energetic grounds that these particles must be formed in a dense, when the top of this set of energy levels for the neutron, the so-called Fermi C, exceeds the mass of the lambda, and that's certainly the case at the center of a neutron star. Now, what I'm showing here is the equation of state with just neutrons and protons, or neutrons, protons, and hyperons. This is the units we work in, but for those of you who like engineering units, this is Pascal, and the pressure is 10 to the 35, or about 10 to the 30 atmospheres. 10 times more than I described to you earlier at this point. And down here is the density, and this point is 3.5 times the density in the center of a nucleus. And that's where the hyperons enter the equation of state for the reason I just explained. And now you see the pressure is lower when you add the hyperons. And I should have put an acknowledgement to Jess Leong, student who produced this curve for me. But I got it very late, so I didn't have time to do that. When hyperons appear, they have low momentum. And that's the reason that the pressure doesn't grow as fast as the density goes up. But if the pressure doesn't grow as fast, the maximum mass of the neutron star is lower in the theoretical calculations. And most state-of-the-art calculations until 10, 15 years ago suggested that you couldn't form a star with a mass greater than 1.6 times the mass of our sun. Because you would form hyperons, they wouldn't have enough pressure, and so you couldn't make a heavy star. And then along came a bunch of observers, Demarest and collaborators, and they found one at 1.97. That was later revised to 1.92 solar masses, but way above 1.6. And if hyperons have to appear in a neutron star, it's impossible that you could find such a thing. And that's the so-called hyperon puzzle, which people still argue about. So this is a summary of quick summary of how they made that measurement. They had a pair, a neutron star and a white dwarf, orbiting around each other. The orbit is at 89 degrees, so it's almost in a plane looking at us. And so as the neutron, if the neutron star is on the side of the orbit towards us, the waves come to us, the radiation comes to us unperturbed. But if it's the other side of the orbit and the white dwarf is here, the light has to go around it. And it takes longer to go around the white dwarf than to come straight to us. And that delay is called the Shapiro delay. And you see here an illustration of the delay when the neutron star is behind the white dwarf and we're over here. And from that delay, one can work out the mass of the star. And in their paper in Nature, they claimed that it ruled out the occurrence of hyperons because it was much larger than 1.67. Now, in fact, with a couple of co-workers, we'd published a paper saying that you could have hyperons, but they ignored that, of course, because they wouldn't have gotten to Nature if they'd mentioned it. The solution to that puzzle seems to be that when you have very dense matter, it's not just the force between two particles that matters, but when two strongly interacting particles come together, they change the internal structure, and that changes the interaction with a third particle, and that's called a many-body force, and it arises naturally if structure changes in dense matter. Now, just to show you that the theoretical curves I'll show you are in agreement with experimental data as far as we have it on Earth. There are 820 roughly known nuclei with even numbers of protons and even numbers of neutrons. What's shown here is our theoretical calculations. Kay Martinez was a student here in Adelaide. She's now back in the Philippines. And what you see, the coding here in the bottom curve, is the deviation of the absolute binding energy of a nucleus with a given number of protons and a given number of neutrons, the difference between the theoretical calculation and the experiment. And down here, you see the purple is 0.1%. So in most of this region with more than 60 neutrons and more than 40 protons, we're within 0.1% of the binding energy. And in comparison with other theoretical models, it actually does much better. The only one that's slightly better, FRDM, has 27 parameters and it can't predict other properties of the nuclei. In Nature Physics, just a few years ago, there was a so-called model-independent estimate of the equation of state. That's shown by the blue and green. The green is the preferred area, and what I'm plotting is pressure versus energy per unit volume. So the green is where they think on model independent grounds the equation of state should be. Remember, equation of state is pressure as a function or versus the energy density. And our calculation is the black line. So it's in perfect agreement with that. But their argument was that this kink, which for us comes when hyperons appear, comes from a transition where protons and neutrons disappear and we have quark matter. And so that's another controversy in this field. Do we have quark matter, where quarks are no longer sitting inside individual protons and neutrons, but they percolate through the whole core of the star? In the calculations that I've shown you, these are the percentages of various particles as the density goes up. And you see initially we have almost all neutrons, which are in blue, almost 100%. We have a few protons, actually reaching as much as 10%. Electrons balance the charge of the protons along with negative muons. But once we get up to 3 times the density of a heavy nucleus, we get a lambda particle appearing, and then particles with even more strangeness. Perhaps something that makes a little more physical sense is if we look at 3 different models of the structure of the core of a neutron star as a function of the distance from the center. So 0 is the center of the star, and this is the distance in kilometers. And all of these models produce stars which are of order 12 kilometers in radius. And you see at large distances, all agree we have neutrons and protons, but you see in what's even as far out from the center of the core as 5 kilometers. Okay, that's here to the other side of Prospect. It's not just neutrons and protons, but there are strange particles there. Particles containing strange quarks, a sort of matter that we can't have here on Earth. I just find that remarkable. Now, I'll come back to how we learn about properties of neutron stars very soon, but I did promise in an earlier abstract to say something about the dark side, and so I'll do that, because neutron stars, supernovae, play an important role in our knowledge of the dark side of the universe. I'll just remind you, we've learnt that ordinary matter is only 4%. This is the stuff we understand pretty well. 4% of the energy in the universe. And then we have dark energy, which we don't understand, but it's 73%, and dark matter, which is something like 23%. And we have no idea what dark matter is or what dark energy is. We know that dark matter interacts very weakly, but it has important gravitational effects. The evidence for dark matter is illustrated here. So this is the velocity of stars as a function of the distance from the center of a galaxy. And if the matter in the galaxy was just what we could see, this is what we would expect. It's not a very good fit to the data. In order to understand the data, we need much more matter than we can see, and that's the dark matter. We don't know whether the problem is a problem with gravitation, with our theory of gravitation, with general relativity, or whether there are new particles. The Centre of Excellence for Dark Matter Particle Physics, which involves the University of Adelaide, Melbourne, and many other places in Australia, is looking for dark matter if it's a particle. Could be completely wrong. It might not be, but we've got to look. And one of the things being done within that centre is to build a laboratory in Stawell, in the gold mine there, 1,000 meters underground, to get away from cosmic ray background to look for dark matter. And here you see the entry to the tunnel and a hall, and a cave at 1,000 meters underground, which has now been turned into a laboratory. I haven't shown you the most recent pictures, but there's a laboratory there and an experiment being built to look for dark matter. One of the exciting things that we can learn from neutron stars about dark matter, what's shown here is the strength of the scattering of dark matter from protons or neutrons against the mass of the dark matter particle. And experiments like the one I just mentioned in Stawell, the Stawell Underground Physics Lab, can look in this region. But when we go to masses out here or masses down here, we can't use that sort of experiment. But by looking at the capture of dark matter on neutron stars, we can hope to put limits which are given by these curves. So looking at the heating of a neutron star as it gets older can give us information about the dark matter particles captured by that neutron star. That's pretty exciting. For dark energy, well, we don't really need neutron stars there, but we do need supernovae. I told you that if the mass of an exploding star is less than 8 solar masses, it leads to an explosion. We see carbon and oxygen and some iron and cobalt released, but no really heavy elements. That's type 1a supernova. It happens when a white dwarf reaches a mass above the Chandrasekhar limit, so about 1.4 solar masses, and explodes. Otherwise, it would just sit there as a boring, stable little particle, a little star. But if it accumulates mass, it can explode. And the point is, because they explode with a very accurately known mass, they could serve as a standard candle. And by looking at a type 1a supernova in the distant universe and looking at how bright it is, you can see how far away it is. And so what this shows is by measuring the redshift, which tells us its velocity, and the brightness, which tells us the distance, we can see that when you get far away from Earth, from our galaxy, the expansion of the universe is actually increasing. It's accelerating. And that's the explanation for that. And it's an explanation that's sort of stupid because we don't know what the stuff is. But you need something called dark energy, which tends to push the universe apart. And the evidence for that comes from supernovae, but I haven't said much about it because they don't produce neutron stars. So how do we study neutron stars? Well, there are two really exciting things which are recent developments. The first is the Neutron Star Interior Composition Explorer. And like all acronyms in particle physics or nuclear physics or astronomy, it's a little bit stilted, but they wanted nicer as the abbreviation. So Neutron Star Interior Composition Explorer. And it's 56 gold telescopes on the outside of the space station. What they managed to do was look at a couple of neutron stars and watch them rotate by looking at hotspots on the surface of the neutron star. That's remarkable. Neutron stars are such compact objects, but still heavier than our sun. And so light emitted from parts of the back of the neutron star can be bent around and we can still see part of the back of the neutron star because the light is bent as it leaves. And so they've studied one neutron star in the mass range about 1.4 times the mass of the sun, which is a pretty much garden variety neutron star, and one heavier neutron star at about 2.1 solar masses. And they've deduced the radii of the neutron star by modeling the emission of the light as the star rotates. And hopefully the next, will this rotate? It does take a while, does it? Okay. So I should click. Yeah, that's why I don't like using anything but my own computer. But okay, ideally, this little movie would show us these spots on the star revolving, and what's analyzed is the signal showing the motion of the hot spots on the star. Okay, too bad. And the second new way of getting information is from these remarkable experiments, LIGO and Virgo in Europe, LIGO in the United States. But University of Adelaide researchers, along with others in Australia, are an important part of those experiments. Well, the LIGO experiment in the States, where there are two detectors. And what they discovered in 2017, 17th of August 2017, was a signal as two neutron stars, which were orbiting around each other, finally ran out of steam and ran into each other. And these blips, which I don't pretend to be able to interpret, are the product of an interferometer with arms of several miles, and the change in the interference fringe is caused by a change in length. So as the gravitational wave goes by, one arm gets shorter, the other gets longer by 1/10⁻21 centimeters. So it's hard to believe that the change in length is so small, but we can see the change in space-time as the gravity wave produced by the merger of two neutron stars as it goes by. Now, what's happening? There we are. I have a little picture here of what's going on. As the two neutron stars are about to come together, they're orbiting each other, they get closer and closer. As they get very close, the pull of one is so strong that instead of being spherical, they become slightly football-shaped. And the amount that they're football-shaped can be measured from the shape of the gravitational wave signal. And so that's called the tidal deformability. And from the one measurement, we have this limit, and you see it's a pretty big limit on lambda. And you see some recent calculations which agree with that. But as we get much better data from future experiments on LIGO and Virgo, the errors on this will come down, and we'll see whether these predictions survive. Now, let me just go back. So this is solving those equations I showed you back at the beginning, the Tolman-Oppenheimer-Volkoff equations. You see here, for a given mass, so say 1.4, which is the one observed by LIGO Virgo, or one of the stars observed by them, the box shows the limits deduced from their data on the radius for that mass star. And the nicer data on the heavier neutron star, the box shows the errors on their constraint, that shows their constraint on the mass, on the radius for that mass. And here you see the predictions for the radius of the star versus its mass without and with hyperons. So the blue one's the one we believe in. And you see at the moment it's consistent with those. But as we get more and more data, we'll see whether this survives. Now, the last thing I wanted to mention, and hopefully we're not too bad for time, is that the observation of the merger of these two neutron stars has given us completely new insight into the origin of heavy elements. These pictures are pictures of three different, so Tycho, Kepler, Cassiopeia, supernova. And the colors reflect what elements are being seen in the mess that's in this mess that's exploded out from the supernova. And so red means it's iron. So we can see there are bits of iron here, bits of iron there. Silicon is green, and calcium and iron are blue. So there's a lot of iron. But there isn't much that's heavier than that. And yet our periodic table is full of elements heavier than that. And so it's been a problem for many years that supernova were the only things we could think of to make heavier elements, but it didn't quite work and we didn't quite see them. But now the measurements made by astronomers following the gravitational wave signal from GW 170817, that merger, show that you actually can make much heavier nuclei when two neutron stars merge. And so here's a relatively modern periodic table. This color is elements that are only made in the lab. They don't exist naturally. And in fact, it's a bit out of date because the highest element now is 118. So a nucleus with 118 protons. Okay. But what we see is the yellow is exploding stars. Exploding white dwarfs, the gray. So you see we get iron, cobalt, nickel, up to zinc, but not much beyond that. And then we get merging neutron stars. And this is based on measurements made of the cloud of debris surrounding the merger of the two neutron stars in 2017. And you see that when we get to heavy elements, including gold, and where's silver? What else are you interested in? Platinum. Almost all of that is made when two neutron stars merge and explode. So the statement that we're the stuff of stars is actually as true as it could possibly be. So, to make our chairman happy, summary. If I haven't convinced you by now that these are amazing objects, then I'm sorry. They're formed in supernova explosions, and we couldn't have them without we couldn't understand them without quantum mechanics. A point on the surface of a neutron star is rotating at 200 million kilometers an hour. It's just impossible to imagine this environment. We've seen that mergers of neutron stars, where they come together and then explode, leave behind a neutron star, possibly, or if the stars are heavier, they might leave behind a black hole. And we actually don't know what's left behind after the 2017 merger. But we know that most of the heavy elements that we've come to know and love are made when two neutron stars merge. The maximum mass and accurate values for the radii of neutron stars are not known. And that's crucial from the theoretical point of view in terms of our understanding of dense matter. The nature of the matter in the core is not known. I talked a little bit about the hyperon puzzle, but equally fascinating is whether the core of these neutron stars contains quarks that are free to move and aren't confined in individual protons and neutrons. The real excitement is that there's so much more information promised by LIGO and Virgo, whose sensitivity should be expanded. The range, the volume of space they can look at, LIGO can look at in the near future should be maybe 10 to 100 times greater. And so we should see many more events, as well as NICA, and there will be other experiments. We can't understand these things without understanding quantum physics, without the astronomical observations, clever observations, clever instrumentation, without understanding gravity and nuclear and particle physics. And that's what makes them so exciting. Some of the work I mentioned involves many people, and I've shown a few of them here. Thank you.
Thank you, Tony. I think Tony would be happy to take some questions.
Don't be shy.
We have a runner coming towards you, so.
You mentioned hotspots on the surface of the neutron stars. I imagine there's no fusion still going on in them. Is that from just matter infall and spreading on the surface?
That's the idea.
Okay, tough.
How far away is the closest one?
I think it's at 400 light years. But I may be wrong. I'd need to check it. As I said, I'm not an astronomer, but that's my memory. Gary, do you remember? No?
In regards to the Hyperon puzzle, if it does turns out to be true that neutron stars do have hyperons in their core, does that have any significant implications for the way we understand neutron stars and what they can do, and how that affects when two neutron stars merge together?
Well, sure. It'll give us confidence that we understand the equation of state, so energy density versus pressure. It'll give us a hint that we don't have a transition to quark matter. Why that is, I mean, we really have very little in the way of theoretical understanding of what quark matter would look like. And so that's another reason these things could be exciting. It could be there's a transition to quark matter. In collisions between nuclei at CERN and at Brookhaven, you also make matter with very high temperatures. And there you do form a phase where quarks run free. But that's at very high temperature. And neutron stars, when neutron stars are formed, they can be quite energetic, maybe at 10 billion degrees Kelvin. But pretty soon they cool down. And most neutron stars that we see are maybe 600, a few 100,000 degrees Kelvin.
Any other questions out there?
Thank you. I was wondering, eventually every neutron star must run out of energy, eventually. Do we know any objects
Well, it doesn't
that stop rotating,
it doesn't
that
need,
stop radiating?
Yeah, it doesn't need energy. It's just sitting there, basically. I mean, if it eventually, I guess it'll stop spinning, but that could take billions of years. I mean, it's the most dense thing it can be. There's nothing much else it can do. So it's just going to sit there.
Thank you.
Might become less interesting once it stops spinning because we're not going to be able to see it. We won't have any radiation coming from it. So it'll just be a blob. We might be able to see it by light being bent past it. I mean, that's one way of looking for small black holes, for example, which might be one explanation for dark matter, but doesn't seem to work.
Professor, you mentioned the you mentioned the Pauli exclusion principle for neutrons. Did this come? Sorry, just a history question. Did this come out of work with the Bohr model of the atom?
No, Bohr was really before quantum mechanics was understood. It was a bit of sleight of hand, very clever, but it wasn't quantum mechanics. And even when quantum mechanics was invented, it took a while to understand that there were two kinds of particles that we know. Particles for which there is no exclusion principle, they're called bosons. So photons, pairs of electrons, Cooper pairs, which give superconductivity, things with spin, intrinsic spin. Sorry, I can't give another description, which is integer. You can have any number of them in the same state. But particles with half integer spin, like the proton, neutron, electron, muon, there you can only have spin up and spin down particles with the same wave function. If that wasn't true, we wouldn't have atomic structure. Atoms would be a mess. All the electrons would be in the 1s state, and it would be a bizarre universe.
So with reference to the quark matter, that could potentially be, I was wondering, like, what condition inside the neutron star could cause it? Would it be the density, the energy due to the momentum in there? Like, would it be like an almost like decomposition of the neutrons and protons?
Well, the proton is about 10 to the minus 15. 1 Fermi is the unit. It's called a Fermi, FM. Femtometer, if you like, standard units, but everybody calls it a Fermi, which is also FM. And that's 10 to the minus 15 meters. The proton is 10 to the minus 15 meters in size, in radius. At the densities of the center of a neutron star, they sit partially on top of each other. So to think of the quarks being entirely confined in one and entirely confined in the other, when the damn things overlap, sooner or later, the quarks are going to move between them. And that's a matter for intense study. And there's no conclusion as to when you get a whole bunch of protons and neutrons together, when those boundaries will break down.
Very interesting talk. Lots of questions going through, but just one thing occurred. You had the layers of energy levels of 2 at each one for the neutrons. Is that just due to the opposite spins, or what is it?
Each level can have 2 spins. William again.
Sorry, I just had an extra question about quark matter.
Don't be sorry, but there's a prize for 2 questions.
So we understand that with color confinement in QCD, that so quarks are bounded together, but if you try and add energy to that to separate the quarks, the amount of energy that you put in would form another quark that would replace the one that you tried to separate. So how come the same thing doesn't happen in what you say of like extreme conditions where quark matter would run free? Wouldn't that energy that you put in to separate the quarks just make new quarks and then rinse and repeat?
It's good question. What matters is, well, that the color degree of freedom carried by the quarks, the total wave function has to be a color singlet. If that's the case, then the energy is finite. So that, I can talk about it later, but that's the answer.
Thanks.
Thank you. This question is sort of an amalgam and lead on from most of these other questions. Is there anything that we see with neutron stars that approximates the evaporation that we're seeing in black holes, or they just sit there and slowly
The evaporation you see one?
The evaporation out of black holes with Hawking radiation. Anything similar to that, or do they just sort of sit there and slowly accumulate?
They're much more boring in that sense.
Yeah.
I mean, they're pretty exciting things, but they don't do that. Yeah, the radius is much bigger than the Schwarzschild radius.
Okay, we seem to have run out of questions at this time, so I think we'll wrap up at this stage. But it amazes me how many fields of physics have to come together to make sense of it all. And I think it's entirely appropriate that we have one of the most senior physicists in our state, Tony Thomas, as Elder Chair of Physics, come and talk to us about all the fields that he's aware of under his belt. Thank you. Can we please thank Tony in the usual way? And as a small token of our appreciation from ASA, I hope you enjoy that one. Thank you, Tony. Thank you very much. Was this a slide left over, Tony? Okay, well, you can catch. You can read the paper, and as I will allude to, we've had our questions. We will be able to have Tony's talk available on our YouTube channel, so you can see the missing slides for yourselves and do your own homework. And along with a number of other distinguished speakers we've had in the past. So please be aware of our YouTube channel, youtube.com/astronomy SA. A lot of good stuff there. In particular, just off the press is the sky this month for March, done by Paul Martinitis. He does a great show of what there is to see up there right now this month and into April. Well worth checking that out, and that is also on our YouTube channel, youtube.com/astronomy.sa. This month we have seen some activities already take place earlier this month, but we have a casual Friday with Brian Homan, 14th of March for members, 7:30 p.m. A get together via Zoom. Members, watch your ASAChat emails for links there to get into that. We have member viewing nights coming up at Stockport, 1st of March. I think that's come and gone already, but 22nd of March for the 3 sites we're engaged with, being Stockport, our own site, and Tuparang and Meldanda. So watch out for the ASAChat emails to members. And the Astro Imaging Special Interest Group, the largest special interest group in ASA, meets online by Zoom. And again, members, watch out for the ASAChat links and notifications about that Zoom session coming up on the 11th. But for the public, we have our next star party on Saturday the 3rd of May, and we also have a session at Hawthorndine, which I neglected to put on the list here, but that comes up on the 21st of March, a Friday night, 21st of March. Keep an eye on our website. They've been a great introduction to astronomy and using telescopes for members of the public, to which we gather and bring our instruments of various types and sizes. So if you're at all interested in astronomy, buying your first telescope, for instance, that's a great place to come and see what people use and ask questions and see what there is to see. In terms of member nights, one of the benefits of members is members getting together to do their thing. Various photos there of our last members night at Stockport on the 1st of March. You can see various members doing their thing visually and photographically. And for those who are unaware, we rely on red lights to preserve night vision. So you can see them in action there because most of the illumination is via red lights and the odd computer screen. So yeah, if you come along to our public nights as members of the public, we do stress low light levels and particularly red lights pointing down at the ground, seeing where you're going, being key to preserving night vision. ASA Council has a bunch of names there, but of note are the vacant positions. And some of us are sharing a number of roles at the moment. Myself and Assistant Secretary are covering for the Secretary. And it's quite a task for us to try and cope with. We would really appreciate some help out there in terms of secretarial support who can monitor our contact email addresses and get involved with seeking answers for the public who seek answers to their questions. So it's not too much to ask, I hope, but a task divided is a task made easier, and we certainly look for support from our members. So if you've gained benefit from ASA as a member, then please consider stepping up and contributing something in return. We have information sheets and merchandise at the back of the hall. See Rosemary, Andrew and Nicola for further information there. We thank our sponsors, Adelaide Optical Centre and Bintel. As members, please consider shopping there for your next astronomy purchase, and mention you're from ASA because discounts are on offer. I've harped on enough about membership, but clearly you can see via the dots on that page, the membership is worthwhile with a lot of services specifically exclusive to members. And from my personal perspective, I really enjoy the Dark Sky Astro Camps, which are only available for members to enjoy. A great great times to be had at those events under the stars, always under a dark sky. We have various social media channels, Facebook, again, /Astronomy SA, YouTube, which I've spoken about, /Astronomy SA, Instagram and Twitter, which we're also put out the odd relay message on. So if you're in those channels, subscribe to them for updates. I thank all our volunteers tonight, particularly Brian, who will be looking after supper shortly. And as I've said earlier, we always look out for volunteers. Thank you for joining us this evening. Tea, coffee and supper available in the foyer. I'll close the meeting at this stage. Thank you all for attending.